So the first part we looked at in thermochemistry was calorimetry. Remember, that's a way to measure the enthalpy change for reactions that can't be measured indirectly. So it's a direct way to measure it, or a way to inference it. And so when we look here, it says, what is the molar enthalpy of combustion of ethanol? That's the purpose of the experiment. And the thermometer, water, and the aluminum calorimeter are the surroundings. The system, which is the combustion of ethanol, is going, and as that's happening, the heat is being transferred to the solution in the water aluminum calorimeter. Now, we have an ideal versus real calorimeter. For ideal, we assume that there's no heat transfer to the aluminum can. Of course, in the real world, everything absorbs heat. And so that would be the thermometer itself and the actual material of the calorimeter. So because of that, we need the actual specific heat capacity, or the C, the mass, and the change of temperature has to be for the whole entire calorimeter itself. So everything that essentially makes that calorimeter. And so we do need then the maximum temperature change of the water, the mass of the calorimeter, of the aluminum one, since it would actually absorb heat, the mass of the calorimeter and the water, okay, so that you would have a combined mass for your thermochemical equation. And then we want to know the mass change of ethanol, and that's because, remember, we want the molar enthalpy of the ethanol change. So that being said, 1, 2, 3, and 6 would be appropriate here. Now for this one, which is more of a calculation question, we have the molar enthalpy of combustion that gives us a negative 810.4 kilojoules per mole when 0.285 moles of the substance is burned in the calorimeter containing 8.60 kilograms of water. The increase in water temperature is, so we're looking for the temperature change. Now, what we need, remember, is the calorimeter equation, because we're dealing with masses given and temperature change. But we're also dealing with molar enthalpy, so we'll use the equation where the moles multiplied by the molar enthalpy of reaction is equal to the negative mc delta T. And we could also use the ratio for the specific heat capacity, where 1 kilogram over kilojoules per degree Celsius instead of joules over degree Celsius. And this is because we give you the mass in kilograms and we give you a molar enthalpy of reaction in kilojoules per mole. So plugging in all our variables that are given here, and again, we use that ratio, we simply isolate for the temperature change. And after plugging that into our calculator, we get a temperature change of 6.4 degrees Celsius. Now, what happens when we have molar enthalpy of reaction questions without calorimetry? Well, a lot of the times we'll have to use proportion. So we have inside this photosynthesis equation here, the enthalpy change given inside the equation. The left side tells us that it's endothermic. And then they tell us that the amount of CO2 required to absorb 2.2 times 10 to the 3 kilojoules. Well, that now changes the energy. And remember that the energy in the equation becomes part of the chemical equation, and we're talking about in terms of the mole ratio. So that's 2,802 kilojoules per 6 moles of carbon dioxide is equal to, well, 2.2 times 10 to the 3 kilojoules over, well, how many moles? So if we isolate for the amount of moles, we plug this in, and we can call this X. We would have X multiplied by 2,802 kilojoules per 6 moles of CO2, and that's equal to 2.2 times 10 to the 3 kilojoules. We simply just simplify the left side of the equation. And when we do that, we divide both sides by 467. We end up with a value of about 4.71 moles. And this makes sense because if the energy is less, then the moles consumed should be less as well, since they must be balanced. So here, when ammonium chloride is added to water, the solution feels cooler to the touch. And that point, cooler, is extremely important because that tells us that this reaction is endothermic. The statement which best describes this observation is, we got to think about, what does it mean to be endothermic? Well, your enthalpy change is positive, which means that the enthalpy change should be written in the reactant side of the equation. So if we look at B and C, none of those values or meanings reflect the reaction being endothermic. So the only one that has the enthalpy change term written on the right side would be option D. And so this would tell us that it is endothermic. And given everything that we have here, that would be the most proper response. So here we got a description of the cold and hot packs, and each of these contain an inner ionic solid, right? So when they dissolve, either the solution is going to release energy or absorb energy. Now it says here when ammonium nitrate dissolves, your water temperature decreases, and when the calcium chloride dissolves, the water temperature increases. So for the hot pack, where the water temperature increases, that is going to have to be an exothermic reaction. So out of the four options given here, A would make sense because that is telling us that the process is exothermic. Now, if we're thinking about which of these graphs would match the information given above, well, remember that endothermic has to go upwards because the system itself is gaining potential energy. And so that wouldn't be correct for calcium chloride since we already decided that it's exothermic. And for ammonium nitrate, that wouldn't be right either because the graph going down for option B would mean that it is endothermic. So option A, which shows the energy going upwards, is the most appropriate option in this question. And that's because the system gains potential energy in an endothermic reaction. Now, when we think about calorimetry, we remember that every reaction has an enthalpy change, right? A change of potential energy as reactants are converted into products. And sometimes that change is negative, meaning it's an exothermic reaction. And sometimes that enthalpy change is positive, where the reactants have gained potential energy as they are converted into products. Now, there are some reactions, because they're too fast or sometimes too slow, that it's really difficult to measure the enthalpy change of them directly. And so what we can do is, because energy is conserved, we can take our enthalpy changes of known reactions, ones that are reasonably easy to test and to abstract the enthalpy change value for, and we can use those to get the reaction that we want. Now, the reactions that we use, or the useful reactions, or the reference reactions, are ones that must be related to the target reaction, or the one that we're actually trying to get. And so you have to prove that if you add up all these reference reactions and cancel out any like terms, that they got to equal the reaction in question, or the target reaction. And this law of addition is what we know as Hess's law. Now here are the reference equations, and we performed the first two equations in this kind of set here for Hess's law. Now the third one is way too dangerous to do, so we're just going to use a generally accepted and repeated value of the formation of water. And so using the calorimeter data from the polystyrene cups that we used, we're going to plug in the data for the first two equations here. And then we're going to have to do some proportions, because remember that those weren't given per mole, okay? So again, MC delta T for each one, and for the first reaction, that's going to be per 0.25 grams, and for the second reaction, that's going to be per 0.5 grams, but we're going to do some proportion math in order to get it per mole so that can represent the actual full equations. Now, with our calorimeter data, we're plugging those enthalpy change values into our reference equations. And now we're going to set out to prove equation 4 here, or the target equation, which was the reaction that you saw in the beginning. Now, I want to get the products of that equation. So the best thing to do first would be to try and get magnesium oxide. And I can see that that's in the first reaction, but it's in the wrong place. So we're going to reverse that equation. Next, if I go to prove, let's say, the oxygen, well, that's in the third equation, and it's in the right place with the right amount, so we're not going to change anything. We're going to leave that equation. And then we're going to prove the magnesium portion of the equation, which, if we look at equation 2, it's also in the right place and in the right amount, so we're going to leave this. Now we're going to write all of these reference reactions as one giant reaction and simplify it by canceling out terms on both sides, or the like terms on both sides. And if it does simplify to the final target reaction, then we know we've done all the right moves and we can simply add up the enthalpy changes. So I can see here that the MgCl2s cancel on both sides, the water liquids cancel and the HCl's cancel, as well as the hydrogen gases, and that leaves us with magnesium plus half oxygen, which gives us magnesium oxide, and that is proving the target equation. So now we can just add up those enthalpy changes for our total enthalpy change of this reaction. So we have another Hess's law question here, and we can tell from the reference reaction that it gives us. So we want to find out what the enthalpy change of reaction is for A solid plus half D2 gas, which yields to AD solid. So we're going to solve for AD solid first, and I can see that it's in the second reaction here, but it's in the wrong place. So we're going to reverse that reaction. Now remember, when you reverse a reaction, you have to also reverse the sign. Next, we're going to look for the half d squared. I could see that it's in the third equation here, third reference equation, and it's in the right spot, so we're going to leave it. Next, if we're solving for A solid, it's in the first equation, and it's also in the right spot, so we're going to leave it as well. Now, again, being sure to reverse any signs of equation that were flipped, we're now going to add all these reference equations into one giant equation and cancel whatever like terms appear on both sides. And hopefully, once we've simplified this, it will simplify to the target reaction that we want the enthalpy change for. So once we write down everything that is left over, that gives us A solid plus half D2 yields to AD solid, and that is the target reaction that we want, so it's been proven. So now we can add up all the enthalpy changes based on the changes that we made to each reference equation here. And when we do that and we plug that into our calculator, we see that we get an enthalpy change of about 49.3 kilojoules. And that's positive, meaning it's endothermic.